Today we'll discuss techniques for sampling from a distribution, and we'll also begin our discussion of statistics. The reason you would want to be able to sample from a distribution is that you have a distribution of interest and you have some random experiment that involves random variables with that distribution. If you want to explore properties of that random system by simulation, then you're going to need to be able to draw independent samples from that distribution. And the main idea for simulating from a distribution on the real number line is something called the inverse CDF trick. And the idea is that you draw the cumulative distribution function of the distribution of interest. So this is the function which tells you how much probability mass is to the left of a given point x. For example, if this is the probability mass function of a given distribution, so it puts a little mass here, more mass here, and more mass here. So such a random variable would be always equal to one of these three values, and most frequently the one in the middle. Then the cumulative distribution function, you want to think of it as starting from the left, where you've accumulated no mass so far. And then when you hit this value, you will have accumulated an amount of mass equal to the height of that bar. And then as you move, you've accumulated still that amount of mass, but no more. And then when we hit this point, we jump up to a height which is the sum of these two red bars, and so on. And we consume the last bit of probability mass here, and then the CDF is going to be at 1 forever after. And the idea of the CDF trick is that you generate a uniform random variable between 0 and 1. And you move left and right from that position on the y-axis until you hit the CDF graph, and then you go straight down. For example, if we generated this value as the output of our uniform random sample, then we would move to the right until we hit the graph, and then we go straight down. And we would return this value for our random variable x. Or if our output u was here, we would go left and right until we hit the graph, and then return that value for x. So you can see that this makes sense in this picture, that you can only get these three possible values for x, because the only way to hit the graph moving left and right is to do so along one of these three vertical dotted lines. And it's the same idea if you have a continuous distribution, like in this picture, we have the cumulative distribution function of the standard normal distribution. And we generate a uniform random sample over here on the left, as indicated by this histogram. And so for example, if we generated this value between 1/4 and 1/2, we would move to the right until we hit the graph, and then we would go straight down, and that would be the output value we return. And when you do this, it effectively transforms this uniform distribution into whatever distribution is represented by your cumulative distribution function, in this case, the standard normal distribution. So in the first problem, we're going to apply this trick to simulate a random variable whose density function is 2x on the interval from 0 to 1. And we'll check that we've done something sensible by drawing from the distribution many times and plotting a histogram. So let's use SymPy to do some of our symbolic calculations. So first we want to find the cumulative distribution function, and we get that by integrating the density. And we find that the cumulative distribution function is the squaring function on the interval from 0 to 1. So if we do the inverse CDF trick, we'll generate a random variable u, and we'll find the corresponding point on the x-axis and return that value. And since this graph that it's going to hit is the graph of the function y equals x squared, then the point on the x-axis that we return is the square root of u. So this gives a formula for generating a sample from this distribution. We can generate uniform random variables and square root them. So this is our probability density function. We see that our histogram does match up very well with the density. So that looks very good. We feel we did successfully generate from this distribution with this formula, square root of a uniform random variable. So in this second problem, we'll do something significantly more challenging. We'll use the same idea, but to generate from a joint density on the square. So here, there is no cumulative distribution function trick to look at. We're going to have to somehow bootstrap our way from a one-dimensional technique up to 2 dimensions. So you have this distribution function, 3/2 x squared plus y squared. This is what the density function looks like. More massive in the top right corner and less in the bottom left. And the hint suggests that we first draw x from its distribution, which we should be able to do because x is a real valued random variable, and then draw y from its conditional distribution given that value of x that we observed. So we should be able to do that as well because we can take a vertical slice through this density and get the conditional distribution of y given x, and then that will be a single variable that we have to generate, and we can again use the CDF trick. So let's carry this out. So let's again use SymPy. And the first thing we want to do is find the distribution of x, which is not immediately given. We get the joint information about x and y. And in order to find the distribution of x, we need to take all of the mass in this square and squish it all down to the x-axis and accumulate it along this real number line. That will tell us how much probability there is associated with x being some particular value. So we integrate the joint density as y covers the whole square, so from 0 to 1. You get 3x squared plus 1 all over 2. And to find the cumulative distribution function of f, so that's just the density, to find the cumulative distribution function, we can integrate the density from negative infinity up to x, but from negative infinity up to 0 you get nothing, so we can just start from 0. And we integrate that up to x, and we get x cubed plus x over 2. And we can turn that into a function with the lambda phi function. So this x cubed plus 2 plus x over 2, this is a SymPy expression. If we ask what the type is, then we get the sim object. So this is an expression that links into SymPy over on the Python side of the calculation. And if we want to turn that into a Julia function we compute with, we use this lambda phi function. So then to use the inverse CDF trick, we need to find the inverse of this function. In other words, we need to be able to solve for where this function is equal to a particular value. And this is a cubic equation, so it has 3 solutions, and SymPy can tell us what the solutions are. And if we experiment with some particular values, then we'll see that this third one is the one that's consistently coming out to be real. So what we'll do is we'll pick off the third solution and turn that into a function. So now we can generate 1,000,000 observations from the distribution of x and see how we're doing. And this looks pretty good. It's quite close to the density of x. So that checks out. So now to generate y based on the value of x that was generated, what we need to do is for any value of x, we need to be able to sample from this distribution that we get by slicing this joint density. And the distribution you get by slicing the joint density, it essentially is the joint density, except that you have to divide by a normalization constant to make it integrate up to 1. So the density of y given x is the joint density divided by the integral of the joint density along each vertical line. So now we need to come up with the integral of this function along each vertical line. So the integral starts from 0 because that's the bottom edge of the square, and it goes up to some arbitrary position y. So we turn that into a function, and we can call it capital F sub y given x. And this formula is a bit difficult to work with in SymPy, so instead we'll calculate it numerically using the roots package. So the inverse CDF is going to be given by finding the 0 of the function which maps each y value to the corresponding CDF value at the given vertical line x minus u. So this solves the equation that the cumulative distribution function along that vertical line is equal to the specific value u, which is going to be the uniform variable we're going to generate. The numerical find root function has to have a starting point, so let's just use a half right in the middle of the interval from 0 to 1. And finally, we can put it all together. So we sample x from its distribution, and then whatever the value of x is, we sample y from its conditional distribution given x. So let's make a 2D histogram of these observations and see if they indeed follow the appropriate shape. To make it look more similar to the picture above, we can supply our own color gradient. So that seems to have worked. In problem 3, we're asked to write a function which starts with a uniform random variable and returns a random integer, which is 1, 2, or 3 with probability 60%, 20%, and 20% respectively. And if we look back over at this picture, we can see how the inverse CDF trick plays out with a discrete distribution. We end up for our uniform random variable just checking whether it's below a certain value, and if so, returning the first possible value. Then we check whether it's below the next value and return that one. And then finally, we check whether it's below 1, which it will be at that point if it's not already returned, and then return that value. So we check if u is less than 0.6, then we return 1, so that way 1 will come out with probability 60%. Then if not, we check whether it's less than 0.6 plus 0.2, we get 2 back. And if it falls in that last 20%, we'll get 3 back. And sure enough, about 60% of the time we get a 1, 20% of the time we get a 2, and 20% of the time we get a 3. So in problem 4, we're looking to write a function that draws from a multivariate Gaussian distribution with mean, mu, and covariance matrix sigma given by 2, 0.5, 0.5, 1. And recall the way multivariate normal distribution looks. It's got these elliptical level sets. The mass is more piled up in the middle, and it gets lighter as you move away. So here it is with the white and black color gradient. Mass is concentrated somewhere, and these ellipses can have any orientation. So the mean says where the center of the distribution is here, 1/2, 1/2, and the covariance matrix specifies the covariances of the random variables represented by the two axes. So the x random variable, which is shown here left and right, has a variance of 2. The y random variable has a variance of 1. And then the covariance is 0.5. So this is saying if we put a flag down here in the middle and draw a vertical line and a horizontal line through the middle of the distribution, then there's more stuff going on here northeast and southwest. So each little piece of mass here contributes the product of its displacements from the middle, so the x displacement and the y displacement, and the amount of mass sitting there. So since there's more stuff going on northeast and southwest, you're going to have more of a contribution in that direction and less of a contribution in the other direction. So this is going to be positive covariance, and you have 0.5 right there. So the question is how we can generate a random sample from this distribution, and the key idea is to look at the covariance of a multivariate Gaussian. So remember that we defined a multivariate Gaussian to be a random variable of the form az plus mu, where z is a vector of independent standard normals, and A is a matrix, and mu is a vector. And of course, the mean of x is going to be A times the mean of z plus the mean of mu, and since z is mean 0, this term goes away. And then the covariance of x is going to be the expectation of x minus its mean times x minus its mean transpose. So that's going to be the expectation of AZ times AZ transpose. By linearity, we can pull the A out, and we're going to get expectation of Z times Z transpose times A. And this is the covariance matrix of Z, and Z consists of independent normals 0, 1. So off diagonal, you'll get covariances of 0, and on the diagonal, you'll get variances of 1. So in other words, this is the identity matrix. And we're left with A transpose. So if we have a particular covariance matrix sigma that we want to get, we can do that by generating samples from AZ plus mu, where A has the property that A times A transpose is equal to sigma. And there's a straightforward way to make that happen, because sigma is symmetric. And that means if we can find a symmetric matrix A that squares to give sigma, then A transpose will be the same as A squared, which will be sigma. And if we just define A to be the square root of sigma, then it will be symmetric and we'll have the desired result. So we can square root our desired covariance matrix and then just multiply it by a random normal of length 2 and make a scatter plot of 1,000 samples from the resulting distribution, and we get something like this, which does match up. There's more points in the middle and it fades out as you move away. So let's move on to our discussion of statistics. The key distinction between statistics and probability is that in probability we specify the probability measure. The randomness properties are fully understood and specified as a part of the setup. In statistics, as in the real world, we usually don't have specific reasons to prefer one probability measure over another. Instead, we have to see what happens, look at the real world outcome, and try to infer something about the probability measure that generated those data. And there are many approaches to this. One high-level taxonomy of approaches begins by separating parametric estimation, which involves assuming that a distribution comes from some particular family of distributions. For example, you might assume a distribution is uniform from some value A to some value B, and then you're going to try to estimate A and B. You might assume that it's an exponential distribution with some parameter, or you might assume that it's a Gaussian with some mean and standard deviation, and then you're going to be trying to estimate the mean and standard deviation based on the observations that you see. So that's parametric estimation. And non-parametric estimation is just other stuff, where we're looking at the data, we're not bringing an assumption that it comes from some particular parametric family, we're just looking where the data fall and trying to use that to reconstruct what the probability measure is. So we'll see examples of both of those things. You can think of a particular non-parametric estimator from the examples we've done so far, and that's histogram estimation. A word of caution, though, is that non-parametric does not mean that there are no parameters involved. For example, histogram estimation does involve choosing a parameter, namely the number of bins. In this last problem, we're going to pull in code from this script, mysterydistribution.jl. So we're going to refrain from looking at this code for now. And just based on the values that are returned by this function, we're going to try to say something about the distribution being used to generate those data. So we're generating 100,000 samples. And what we see is that pretty often we get some value that shows a lot of decimal places when it prints to the screen. And also pretty often we get -1s and -0.5s. So if we want to get a better look at this, maybe we'll look at a histogram. And we see that we have quite a lot of probability mass over here at -1 and -0.5, and then the rest of it seems to be spread out. So we can check that there are no other values that appear multiple times. So we're looking for all the repeats here. And what we see is that -1 appears about 40% of the time, -0.5% appears about 20% of the time, and then all of the other values are distinct. So this distribution seems to be mixing a discrete distribution and a continuous distribution. So with probability 40% it returns -1, with probability 20% it returns -0.5, and with the remaining probability it returns a value which is sampled from some continuous distribution. And let's try to get a better look at what that continuous distribution would be. So this very much looks like a Gaussian. If we want to posit a distribution that's responsible for this data, it's very reasonable for us to choose a Gaussian. So let's look at the mean and variance of those data. We find that the mean is about 2, which makes sense because this distribution is centered at 2, and the variance is about 1/4. That's less obvious from the picture, but it's plausible. It means that the standard deviation is the square root of 1/4, which is 1/2. And if we move left and right 2 standard deviations, which would be 1 unit, we would get to 1 on the left and 3 on the right, and that does look like it captures about 95% of the probability mass, which is a property of the normal distribution. So our best guess for what this distribution is doing is deciding with 40% probability to return -1, with 20% probability to return -0.5, and with 40% probability drawing another random variable which is normally distributed with mean 2 and variance 1/4 and returning that value. And if we look at the code, that's in fact exactly what's happening. We get a uniform random variable and it's used to choose between these 3 possible outcomes. And in the third outcome, we get some more randomness and use that to return the final value.